So in 5.7, we're talking about the fundamental theorem of algebra. And even though it's got this big fancy scary name, it's really not going to look much different than what we've been used to doing so far in this chapter. So the first question, of course, is what are we talking about then? If we've got some big scary looking name, it's got to mean something important, right? And it does. It says, kind of formally, that if f of x is a polynomial function, of degree n, so some number degree, then the function has n zeros, at least one of which is complex. So now we're starting to dive into the realm of imaginary solutions. What this means realistically is that actually that's a pretty good way to state it realistically too, right? So maybe the best example then would be to say if my function is x cubed minus 5x plus 3, that has degree 3, which means there are 3 zeros. You know, they're not necessarily unique zeros, right? They could all be the same number. Some of them could be imaginary, but there are 3 solutions in some form. I can write this as the product of 3 factors. So maybe I'll state that too. So just like another example would be to say if I have a function that's 2x to the 5th plus 5x to the 4th, I don't know, minus 3x cubed plus 2x squared minus 10x plus 47. Well, in this entire mess, all that's important is that it's degree 5, which means I can write this as the product of 5 factors, and there are 5 zeros. So that's all it's really saying. The next question is, a lot of students will look at this word fundamental and say, why is it fundamental? You know, what's the point of calling it fundamental? It's, you know, it doesn't set up the basis of other things in algebra, but why is it fundamental? You know, it's fundamental not because it's the foundation of all of algebra, right? Like other things in algebra that we do, like solving equations, like linear equations, or adding and subtracting polynomials, don't really circle around to this, but it does form the basis of a really important part of algebra, right? One of our big topics in algebra, if we were kind of think about this as a map, right, we have all our different topics here. One of the important things when we talk about polynomials is to talk about finding their roots or their zeros. So it's fundamental, it's essential, it's the foundation of solving polynomials and polynomial equations. So that's what it's fundamental about, is now looking at these polynomials and saying, all right, cool, we got a polynomial, but what can we do with it? Well, we can find its zeros, and why is that important? And that's what that's going to start to talk about. In our class, we're not going to delve into too much detail. We're going to try to stick as close as we can to either simple complex roots or just real and rational numbers altogether. Sorry, whole and rational numbers altogether. We're not going to get into too complicated solutions here, but I am going to, you know, show it just to kind of showcase what we're talking about as much as I can. So let's put this to use. Find all of the zeros, not just all of the rational zeros, but all of the zeros of this polynomial function here. All right, well, if we think back to the last section, how did we start? Well, we started with the rational zero test. So, you know, if we dive into our mathematical toolbox, we rely on the prior knowledge that we have. It makes sense then to say, well, let's attack this the same way. So if we start with our rational zero test, P and Q, right? Factors of my leading coefficient, sorry, that's backwards. Factors of my constant, P, factors of my leading coefficient q. So factors of 9 are just 1, 3, and 9. And my leading coefficient is, maybe I'll underline instead of circle, just 1. So factors of 1 is 1. And of course, then my possible rational zeros are plus or minus all of these. And in 5.6, I said after you do this, all we can really do is start testing numbers. So we're just going to start doing that, and we'll do it methodically. Start with 1, start with -1, and hopefully one of those works, so we don't have to work any farther. So synthetic division, I've got enough terms here, right? If I have a third degree polynomial like I do, I should have a third degree term, a second degree term, a first degree term, and a constant, and I do. So I don't have to add any zeros or anything. So my coefficients are just 1, 7, 15, and 9. So I'm going to start just by dividing and going through my synthetic division. So I can already tell this is not going to work. Okay, this number is just going to get bigger and bigger. All right, yeah, so this one doesn't work. So let's try a different one. Let's try, well, the next easiest thing is -1. So let's try -1. Bring down, multiply, add, multiply, add, multiply, add, and we're, oops, that should be 0. That's much better, right? This actually works now. And just like before, I'm trying to keep track of my work. So we've shown that -1 is a 0. My quotient is x squared plus 6x plus 9. And I need to solve that equation too. And I've got a quadratic, right? So I could just jump right to the quadratic formula if I wanted to. But with a polynomial like this, we know how to factor it. So let's just factor it. This is a perfect square trinomial, right? It's in my first term squared plus twice the product plus last term squared form. So this is x plus 3 squared. And if I solve this, x is -3. Now this actually gets into something called a repeated root, right? This square here tells me that I'm actually going to have a repeated root, right? X plus 3 is a factor 2 times. That's what this is saying. So we could state that -3 is a repeated root. For all intents and purposes for us, it's not going to really matter the implications of this, but it is interesting to point out. So my zeros are -3 twice and -1. Right, these are my zeros. So I can prove then, or I can show my fundamental theorem of algebra, right? I have a third degree polynomial, which means I should have 3 zeros. Do I? Yeah, I get -3, which counts twice, and I got -1. 1, 2, 3, 3 zeros. So that's what this is saying with the fundamental theorem of algebra. So let's try one more. One's a little bit bigger, but the process is going to be the same. Find all the zeros of this polynomial here. All right, well, I'm going to start the same way, right? I should still begin with my rational zero test, so I need my p and q. So my p, the constant, factors of 12. I like to be methodical, right? So 1 and 12, 2 and 6, 3 and 4. I've already got 4, I know I'm good. So 1, 2, 3, 4, 6, and 12. And then q, my leading coefficient, just 1, so 1. And of course, that means that my possible rational zeros are plus or minus all of these, 4, 6, 12. So I'm just going to start testing testing zeros. So same thing, we'll start easy. Hopefully one of these works. I don't need to add any zeros in, right? I've got a 4th degree polynomial here. I'll stick with that same color as before. I have a 4th degree polynomial here, so I should have a 4th degree term, which I do, a 3rd degree term, a square, a linear, and a constant. Awesome. So I don't need to add any zeros, so my coefficients are 1, 4, 7, 16, and 12. And we divide. can already tell this one's not going to work out. 28, 40, yeah, nope. So let's try methodical, right? Let's try -1. So 1, 3, 4, oh, this could be it. -4, 12, -12, all right, this works. I'll stick with green. This works. This tells us that -1 is a 0. If I keep track of my quotient, though, I have x cubed plus 3x squared plus 4x plus 12. I don't know enough to factor this yet. Right? This isn't quadratic, which means it's not easy for me to factor. We need to actually keep working here. My goal is, you'll see in a minute, to get down to something that's quadratic. So that way, I can just either apply the quadratic formula or factor it, like we've learned. So we actually have to continue here. And we don't know if any of these zeros are going to repeat, so we have to start all the way over. So we're going to try 1 again. 1. Now my coefficients are 1, 3, 4, and 12. I have a feeling that 1 isn't going to work, but we're going to try it just to be safe. Yep, wait, no, 4. Yeah, this is no good. All right, let's try -1. 2. This one's no good either. All right, let me erase these to give myself some space here. And we unfortunately just have to keep on working. So I don't think 2 is going to work for the same reason that 1 didn't work, right? If I've got all positive coefficients, then if I just keep adding them up, right, that number is just going to get bigger. So we're actually going to skip ahead and try -2. At least this way, I'll be subtracting something instead of adding. So hopefully that'll help me lower my quotient as I go. So I'm going to have -2, -2. Which is 2, -4. All right, that doesn't work. I'm going to avoid +3, and we're going to try -3 instead. See if that works. And this, unfortunately, is the tedious part. Oh, this looks helpful, though. I hope so. 0, 4, -12, 0. All right, we got something. Again, this is the tedious part just because we don't know what's going to work. So -3 is a 0. So now I have 2 zeros figured out. And again, we should keep track of our quotient. So I have x squared plus 4 equals 0. And normally we would say, no, this doesn't factor. But our fundamental theorem of algebra tells me we have to have 2 more factors. They might not be real numbers, but they do exist. So we're going to solve this equation. I'm going to subtract 4 on both sides. I'm going to take the square root, so I get plus or minus. Square root of 4 is 2, and that square root of -1 I need to turn into an I. So now I have my 4 zeros. So my zeros, once and for all, are -1, -3, 2i, and -2i. Whoops. So just to show this with the fundamental theorem of algebra again, 4th degree polynomial, 1, 2, 3, 4 zeros, means we're good to go. Nothing I'm really showing you so far has been new, right? Everything we've done so far is 5.6, just maybe a little more difficult. This next bit is a little bit new. You might have noticed that, if here's 2i, but here's -2i. Why did we get that? Well, when we took the square root during our problem, we have to introduce this plus or minus. So this is something that's actually going to be able to be generalized, and I can say this. So for my complex numbers, I'm going to say if any complex number, remember we used to be able to write it as a plus bi, is a 0, then a minus bi is a 0, right? It's conjugate. If you remember from last chapter, right? It's complex conjugate. The same thing, I guess this should not say rational. This should say irrational, because if I have an irrational number, I'm going to actually be able to think along the same lines. If a plus the square root of b is a 0, then so is conjugate. Just like before, right? Just like we learned when we learned how to rationalize, right? We multiplied by its conjugate. It's because these always come in pairs. So these always come in pairs. They can't go alone. It's like separation anxiety, I guess. Right? They're a package deal. If you got one, you got the other. So using that, a problem you might see, or two problems you might see, is to work kind of backwards, right? So before, we were given a polynomial, and I asked you to find the zeros. Now I'm asking you to work backwards. Here are the zeros, find the polynomial. So my first step is going to be to write these as factors. If 2, actually let's think about it this way. If 2, -3, and 5 are zeros, then my solutions were to say that x is 2, x is -3, and x is -5. Sorry, x is +5. Well, if we were solving these as zeros, and I work this backwards, right? This is x minus 2 is 0, x plus 3 is 0, and x minus 5 is 0. So far, I'm working backwards from the problem that I did earlier. So now I've got my factors, right? If I have all my factors, I can multiply these together. So I'm going to multiply these together to get to my polynomial. So we're just going to FOIL this out. We're going to take it 2 pieces at a time. So let's start with these 2. So if I do, actually I'll keep the same colors. If I do FOIL those 2 out, I'm going to get x squared, and I'll actually show the whole foiling instead of just skipping the step. So let's actually simplify this before we FOIL again. This is going to be x squared plus x minus 6. Now I'm going to FOIL again. Well, I guess it's not technically FOILing, right? Because we have 3 terms in one factor and 2 in the other. So instead of remembering FOIL, I just like to remember that everybody gets a turn. Every pair gets a turn to be multiplied together. So x squared times x, x squared times -5, x times x, x times -5, -6 times x, and -6 times -5 combine like terms. And sure enough, there is my polynomial function. So just to break down the problem, right, of least degree, that means I should only have those 3 numbers as factors, right? I'm not going to go adding any powers to any of my factors, right? I'm not going to make this like x minus 5 squared and x minus 2 cubed. It's unnecessary. Rational coefficients, which means I either have fractions or whole numbers, and I do. And the leading coefficient of 1, right? So I'm not doing anything like making this like 2x minus 4 instead of x minus 2. I have my leading coefficient of 1. If we do this with my second example, I'm going to start the same way. So I'm going to say, whoops, let's keep my color scheme. So my solutions were originally to say x is 4 and x is 2i. But remember that my complex roots, my 2i, has to come in a pair. So if I've got positive 2i, I also need to add negative 2i as a solution. I have to have both. Erase this so you can see better. So that's the only first step I really need to do here. Color scheme, wrong color. So work these backwards again. X minus 4 is 0. X minus 2i is 0. And x plus 2i is 0. This might get a little funky, but it works out, I promise. So just like before, we're going to multiply these together. Now to do this simply, as simple as possible, it's going to get really messy if I try to do like this. I'm going to have i's and x's in places that I don't really want them to be together. So it'll actually be simpler if I multiply the complex pieces together first. So in order to do that, we're just going to FOIL. So I have x squared plus 2ix, yikes, minus 2ix minus 4i squared. Well, fortunately, we don't have to deal with that anymore because the ix's will cancel out. 4i squared is the same as saying plus 4, right? I squared is negative 1. So I'm going to have x minus 4 times x squared plus 4. And we can just FOIL. So x cubed is 4x minus 4x squared minus 16. Let's write this in standard form. So I'm just going to rearrange the squared in the linear terms. And I'm done. Right there is my function. So we can work forwards or backwards here, depending on the information we're given, to either find the zeros or find the polynomial.